We can because we are mathematician yan. I am Teacher Andrew, your soulmate. Allow me to guide you in learning the different concepts and skills in Mathematics 9. We are still on solving equations, and in today's episode, we will deal with equations that can be transformed into quadratic equations. An example of this is the equation x to the fourth power minus 12x squared plus 11 equals 0. This equation is not quadratic because the highest exponent of the variable is not 2 but 4. But we can rewrite it as a quadratic equation. Here's how. We can see that the exponents of the variable x are 2 and 4, where the higher, which is 4, is twice the lower, which is 2. This means we can express the variable with a higher exponent in terms of the one with the lower exponent. So let's say we let x squared be equal to m. It follows that x to the fourth power can be represented as m squared. Therefore, the equation x to the fourth minus 12x squared plus 11 equals 0 can be rewritten as m squared minus 12m plus 11 equals 0. It has been transformed into a quadratic equation. Can we solve it now? Yes, we can. What method do you have in mind? I am thinking of solving it by factoring. Since the numerical coefficient of the quadratic term m squared is just 1, the trinomial has two binomial factors whose first terms are identical, both equal to m. So we must think of two numbers, a and b, the constant terms in the binomial factors. What are our clues? The coefficients in the trinomial should reveal these. The product of the constants a and b must be 11, the constant term in the trinomial. Their sum must be negative 12, the coefficient of m. Since their product is positive and their sum is negative, we can be sure that a and b are both negative. So, what are the two numbers? They are negative 1 and negative 11. Therefore, the factors of the trinomial are the binomials m minus 1 and m minus 11. So we can now rewrite the equation as m minus 1 multiplied by the binomial m minus 11 equals 0. Equating each factor to 0, we must get that the values of m are 1 and 11. And by substitution, since we let m be equal to x squared must be equal to 1, and x squared must also be equal to 11. These are quadratic equations of the form ax squared equals k, where a is 1. So, we can solve for x by extracting square roots. And we must get that x is equal to positive or negative 1, and also equal to positive or negative square root of 11. These are the roots of the equation x to the fourth power minus 12x squared plus 11 equals 0. Let's have another example. We have the binomial x squared plus 2x, quantity squared, minus 2 times the binomial x squared plus 2x minus 3 equals 0. If we are going to square the binomial x squared plus 2x, then we would see that the equation is not quadratic either. The highest exponent of the variable x is 4. But notice that both the first and the second terms contain the binomial x squared plus 2x, with exponents 2 and 1 respectively. The case is the same. The higher exponent is twice the lower exponent. Say we let x squared plus 2x be equal to n. It follows that x squared plus 2x quantity squared can be represented as n squared. So in terms of n, the equation can be rewritten as n squared minus 2n minus 3 equals 0. Our task now is to solve the equation n squared minus 2n minus 3 equals 0. And we can do it by factoring. N squared minus 2n minus 3 is equal to the binomial n plus 1 times the binomial n minus 3. So, the equation can be written as binomial n plus 1 times binomial n minus 3 equals 0. Equating each factor to 0 and then solving for n, we must get that the values of n are negative 1 and 3. Now, recall that we let x squared plus 2x be equal to n. Therefore, by substitution, x squared plus 2x must be equal to negative 1 and 3. So we have to solve these two equations. We first write each in standard form. X squared plus 2x equals negative 1 in standard form is written as x squared plus 2x plus 1 equals 0, while x squared plus 2x equals 3 is x squared plus 2x minus 3 equals 0 in standard form. Both trinomials in these equations are factorable. X squared plus 2x plus 1 is equal to the square of the binomial x plus 1, while x squared plus 2x minus 3 is equal to the product of the binomials x plus 3 and x minus 1. Therefore, the equation x squared plus 2x plus 1 equals 0 will now be written as x plus 1 quantity squared equals 0, which can be solved by extracting square roots. Hence, the equation x plus 1 equals 0. X must be equal to negative 1. The equation x squared plus 2x minus 3 equals 0 can be rewritten as the product of x plus 3 and x minus 1 set equal to 0. Equating each factor to 0 and solving for x, we must get that x is negative 3 and x is 1. Thus, the roots of the equation x squared plus 2x quantity squared minus 2 times the binomial x squared plus 2x minus 3 equals 0 are negative 1, negative 3, and 1. What about if we are given this equation? Such an equation is called a rational algebraic equation. In this type of equation, we see variables in the denominators. And since x is one of the denominators, the value of x can't be 0. Otherwise, the expression 1 over x is undefined. To transform it into a quadratic equation, we should multiply both sides of the equation by the LCD of the rational algebraic expressions, which means we have to identify the least common multiple or LCM of 3, x, and 12. So we express each of these in prime factorization. The prime factorization of 3 is itself, and so is x, while 12 is equal to 2 squared times 3. Let's record these in a table. What are the different bases that we see in these factorizations? We have 3, x, and 2. What is the highest exponent of 3 that appears in these factorizations? 1. What is the highest exponent of x that appears in these factorizations? 1 also. What is the highest exponent of 2 that appears in these factorizations? 2. The LCM of 3x and 12 must be the product of 3 raised to 1 or simply 3, x raised to 1 or simply x, and 2 raised to 2, which is equal to 12x. Thus, the LCD is equal to 12x. So we have to multiply both sides of the equation by 12x. So we have x over 3 times 12x equals 12x squared over 3, which is equal to 4x squared. 1 over x times 12x is equal to 12x over x, or simply 12. 19 over 12 times 12x is equal to the product of 19 and 12x over 12, or simply 19x. Hence, the rational algebraic equation can now be expressed as the quadratic equation 4x squared plus 12 equals 19x. Written in standard form, the equation must look like this. let's use the quadratic formula to solve this derived quadratic equation. In the equation, a is 4, b is negative 19, and c is 12. X equals the negative of negative 19 plus or minus the square root of the expression square of negative 19 minus 4 times 12 all over 2 times 4. So x must be equal to positive 19 plus or minus the square root of the expression 361 minus 192 all over 8. And x should be equal to 19 plus or minus the square root of 169 all over 8. X is equal to 19 plus or minus 13 all over 8. We now split the equation into 2. X sub 1 equals 19 plus 13 all over 8. X sub 2 equals 19 minus 13 all over 8. X sub 1 must be equal to 32 over 8, which can be simplified as 4. X sub 2 must be equal to 6 over 8, or the fraction 3/4 when reduced to lowest term. Therefore, the values of x that make the derived quadratic equation true are 4 and 3/4. And these are also the values that satisfy the original equation, which is rational algebraic. Let's have another example. Let's solve this equation. Equating each denominator to 0, we must get the values of x that will make the rational algebraic expressions undefined. X plus 1 equals 0, so x equals negative 1. 2x equals 0, x equals 0. X squared plus 2x plus 1 equals 0 can be expressed as x plus 1 quantity squared equals 0, therefore x here is negative 1. So it means that x can't be negative 1 because 2 over x plus 1 and x over trinomial x squared plus 2x plus 1 will be undefined. X can't be 0 either because 1 over 2x will also be undefined. So our step 1 is to determine the LCD. X plus 1 is a prime polynomial. 2x is the product of constant 2, which is already prime, and the variable x, while x squared plus 2x plus 1 is the square of the binomial x plus 1 in factored form. So let's record these in the table. What are the different bases that we see in the factorizations? We have x plus 1, 2, and x. What is the highest exponent of the base x plus 1 that appears in these factorizations? It is 2. What is the highest exponent of 2 that appears in these factorizations? It is 1. What is the highest exponent of x that appears in these factorizations? It is also 1. So the LCD must be equal to the product of the quantity x plus 1 raised to the second power, 2 raised to 1 or simply 2, and x raised to 1 or simply x. The LCD may just be expressed in factored form, so it'll be easier to multiply by it later. Hence, the LCD of the expressions can be expressed as 2x multiplied by the square of the binomial x plus 1. Step 2, multiply both sides of the equation by the LCD. 2 over x plus 1 times the LCD is equal to what? By cross cancellation, we must get 2 times 2x times the binomial x plus 1 raised to 1, or simply 2 times 2x times the binomial x plus 1. And the product of these quantities is 4x squared plus 4x. 1 over 2x times the LCD, this equation can be written now as 4x squared plus 4x plus x squared plus 2x plus 1 equals 2x squared. Step 3. Write the obtained equation in step 2 in standard form. By combining similar terms, the left side of the equation can be simplified as 5x squared plus 6x plus 1. If we decrease both sides by 2x squared, we can now achieve the standard form of the equation, which is 3x squared plus 6x plus 1 equals 0. Step 4. Solve the derived quadratic equation. What method should we use to solve the equation? Let's use the quadratic formula. In the equation, a is equal to 3, b is equal to 6, and c is equal to 1. X equals the negative of 6 plus or minus the square root of the expression 6 squared minus 4 times 3 times 1 all over 2 times 3. X must be equal to the negative of 6 plus or minus the square root of the expression 36 minus 12 all over 6. X should be equal to the negative of 6 plus or minus the square root of 24 all over 6. 24 can be expressed as the product of its largest perfect square factor, which is 4 and 6. X is equal to the negative of 6 plus or minus 2 square root of 6 all over 6. The constant negative 6 and the coefficient 2 and the constant 6 in the denominator are all divisible by 2. So, we can reduce the expression to its lowest term by dividing both the numerator and denominator by 2. Thus, x is equal to negative 3 plus or minus square root of 6 all over 3. One last example. Let's solve this equation. X should not be equal to 3, nor should it be equal to 2. 3 and 2 are called the excluded values of x. This is because x minus 3 will be equal to 0 when x is 3, and hence 1 over x minus 3 will be undefined. X minus 2 will be equal to 0 when x is 2, and thus 1 over x minus 2 will be undefined. The trinomial x squared minus 5x plus 6 is equal to the product of the binomials x minus 3 and x minus 2. And so, it will be equal to 0 when x is 2 or when x is 3, making the expression 1 over the trinomial x squared minus 5x plus 6 undefined. So, we go to step 1 now to solve the equation. Determine the LCD. I mentioned earlier that the denominator x squared minus 5x plus 6 is equal to the product of the binomials x minus 3 and x minus 2, which happen to be the other two denominators in the equation. If this is the case, then the LCD of the expressions is the trinomial x squared minus 5x plus 6, or the factored form x minus 3 times the binomial x minus 2. Step 2. Multiply both sides of the equation by the LCD. 1 over x minus 3 times the LCD is equal to x minus 2. X over x minus 2 times the LCD is equal to x squared minus 3x. 1 over the trinomial x squared minus 5x plus 6 times the LCD is equal to 1. Therefore, the rational algebraic equation can be written this way. Since the binomial x squared minus 3x is preceded by a plus sign, we do not need to reverse the signs of the terms in this binomial. So, we may remove the parentheses. Hence, we can write the equation like this. X minus 2 plus x squared minus 3x equals 1. Step 3. Write the obtained equation in step 2 in standard form. By combining similar terms and arranging the terms in descending powers, the left side of the derived quadratic equation can be simplified as x squared minus 2x minus 2. Thus, the equation x squared minus 2x minus 2 equals 1. Then, by decreasing both sides by 1, the standard form can already be achieved, which is x squared minus 2x minus 3 equals 0. Step 4. Solve the derived quadratic equation. X squared minus 2x minus 3 equals 0 can be solved by factoring. X squared minus 2x minus 3 is equal to the product of the binomials x minus 3 and x plus 1. The equation can then be written as x minus 3 times the binomial x plus 1 equals 0. And by equating each factor to 0, we must get that x is equal to 3 and x is also equal to negative 1. However, recall that in the original equation, x must not be equal to 3 and to 2. Therefore, 3 is called an extraneous root. An extraneous root or solution is a solution of an equation derived from the original equation, but it is not a solution to the original equation. Hence, only negative 1 satisfies the given rational algebraic equation. Tagamath, ready your pen and paper. This is Math the Moment. Let's solve for the following equations. Equation number 1, x raised to the 4th power minus 5x squared plus 4 equals 0. For 30 seconds, go! Time is up. Since the equation is of degree 4 and we can express the leading term x to the 4th power in terms of the quadratic term x squared, where x to the 4th is equal to the square of x squared, we can let x squared be equal to another variable, say for instance r. It follows then that x to the 4th power must be equal to r squared. The equation x to the 4th power minus 5x squared plus 4 equals 0 should then be written as r squared minus 5r plus 4 equals 0. And this equation can be solved by factoring and can be expressed as the equation r minus 1 times r minus 4 equals 0. Equating each factor to 0, we must get that the values of r are 1 and 4. By substitution, we have the equations x squared equals 1 and x squared equals 4, which can be both solved by extracting square roots. Hence, the values of x are positive or negative 1 and positive or negative 2. Equation number 2, 4 over x minus 5 over x plus 3 equals 1. For 45 seconds, go! Freeze, but don't get numb, please. The second equation is rational algebraic. Since x and x plus 3 are the denominators, x cannot be 0 nor negative 3. You might have observed that the denominators x and x plus 3 are both prime. Thus, the LCD of the expressions is the product of these denominators. By multiplying both sides of the equation by the LCD, what do we get? 4 over x times the product of x and x plus 3 must be equal to 4 times x plus 3 or 4x plus 12. 5 over x plus 3 times the LCD x times x plus 3 is equal to 5x. 1 times the LCD x multiplied by the binomial x plus 3 is equal to the LCD itself, which is x times the binomial x plus 3 or x squared plus 3x. Therefore, the rational algebraic equation can be written as 4x plus 12 minus 5x equals x squared plus 3x. This means that negative x plus 12 is equal to x squared plus 3x. Applying symmetric property, the equation can be written as x squared plus 3x equals negative x plus 12. By increasing both sides by x and then diminishing both by 12, we must get the standard form of the derived quadratic equation, which is x squared plus 4x minus 12 equals 0. This equation can also be solved by factoring. Let's rewrite the equation as x minus 2 times the binomial x plus 6 equals 0. Equating each factor to 0, we must arrive at the following values of x: 2 and negative 6. Equation number 3. 1 over x plus x over 2 equals 11 over 6. For 45 seconds, go! And time is up. The value of x in the equation must not be 0, since the expression 1 over x will be undefined. Were you able to determine the LCD? Since one of the denominators is x, the LCD must be the product of x and the LCM of the constant denominators 2 and 6. The LCM of 2 and 6 is 6. Therefore, the LCD of these expressions must be equal to x times 6, or simply 6x. So, we multiply both sides of the rational algebraic equation by 6x, and the resulting equation must be 6 plus 3x squared equals 11x. Expressed in standard form, the equation must be 3x squared minus 11x plus 6 equals 0. Let us solve quadratic equation by using the quadratic formula. In the equation, a is 3, b is negative 11, and c is 6. So x equals the negative of negative 11 plus or minus the square root of the expression square of negative 11 minus 4 times 3 times 6 all over 2 times 3. X then must be equal to positive 11 plus or minus the square root of the expression 121 minus 72 all over 6. So x should be equal to 11 plus or minus the square root of 49 all over 6. X is equal to 11 plus or minus 7 all over 6. So x sub 1 must be equal to 11 plus 7 over 6, that can be simplified as 18 over 6, or simply 3. While x sub 2 must be equal to 11 minus 7 all over 6, that can be simplified as 4 over 6, or 2/3 when reduced to its lowest term. Equation solved! And that's it, Kagamath. I hope today's episode has been very helpful. This has been your soulmate, Teacher Andrew. Let me end with this note. Studying all the math concepts and skills can make you an analytical and critical thinker. See you again next time as we face, overcome, and befriend the challenges. We can because we are Mati-Mati Sinyan.